Critical path motion. We have seen examples of CAM design where the position of the follower is the driving component of the motion profile. We'll generally say something like we need to take the position from 0 to 1 inch and 30 degrees of CAM motion. So our focus has often been on the position of the follower. This doesn't have to be the case. Now we will consider a case where the follower's velocity, not its position, is the design criteria. In this example, consider the following statement of critical path motion. We want to accelerate the follower from 0 to 10 inches per second. Kind of a unique statement in terms of what we have seen so far with CAM design problems. Then we want to maintain a constant velocity of 10 inches per second for a half a second. Then we want to decelerate the follower to 0 velocity, return the follower to the start position, and then begin again with the acceleration of the follower. Our cycle time is exactly 1 second. So in this particular case, instead of being told that we want to take our position from 0 to 1 and then we want to maintain that with a dwell for a certain amount of time and then fall again, in this case we're being told we want to accelerate the follower. We're not even told exactly what is going to be the resulting height of our follower. We're just told to maintain a constant velocity of 10 inches per second. So we're also not given any further information than what appears in these first 4 steps: acceleration, maintain, decelerate, and return. For this particular example, we're going to assume that we have 4 segments where beta for the acceleration phase is 30 degrees. The maintained constant velocity happens in 180 degrees of CAM motion. The deceleration of the follower to 0 velocity happens again in 30 degrees, and the return happens in 120 degrees. So just as previous, our total amount of CAM rotation is 360 degrees. Here we kind of have what could be called a constant velocity CAM timing diagram, where we see the acceleration phase here, then we have a constant velocity phase which takes place over 180 degrees of CAM rotation. Then we have a deceleration phase which is 30 degrees. So the 30 degrees of deceleration and the 30 degrees of acceleration are both they both have the same beta. And then we have a 120 degree return phase, where after we have decelerated, we return back ready to accelerate again and begin our constant velocity section. Let's try using polynomials to define the different ranges of motion. For segment 1, we have a rise from 0 velocity to our 10 inches per second. So we're going to focus first right here on this acceleration phase, where we go from 0 to 10 inches per second of follower motion. So when theta is equal to 0, our position is 0 and our velocity is 0. When theta is equal to 30 degrees, notice we did not include an acceleration here at theta equals 0 because we're not coming off of a dwell, and that's one of the reasons why we would set an acceleration equal to 0, or we would do it if we were changing the sign of our acceleration. This is also not the case, and so in this particular example, we are not setting anything for our acceleration. At the end of the acceleration phase of 30 degrees of CAM rotation, we need to have a velocity of 10 inches per second. And at this time, since we want a constant velocity setting now, our acceleration better be set equal to 0 at this time. If it is not, an instant later, we will no longer be at 10 inches per second of velocity. Notice we have not set any value for our position because there's none stated in our requirements. So whatever the polynomial gives us for our position at 30 degrees will be acceptable to us. So here we have 1, 2, 3, 4 boundary conditions. So with these 4 boundary conditions, we'll need a cubic polynomial where 3 is the highest power, and this is our position equation. So here we need to convert x to angular units and also include the angular velocity of the cam to get the absolute linear velocity. In previous examples, we would change this x to theta over beta, this x squared to theta over beta squared, and this x cubed to theta over beta cubed. But in this case, we're not going to do that because we are given this is a critical path or constant velocity cam profile design, and there is a meaning for our x dot in this case, and we're going to see how that's done in a second. The angular velocity of the cam is 2 pi radians per second. For this particular example, we were told that this entire motion would happen in 1 second. An entire rotation is 2 pi. Therefore, our angular velocity is 2 pi over 1 second, or just 2 pi radians per second. So x being theta over beta normally, so our x dot is going to be theta dot over beta, where theta dot is our 2 pi radians per second. So we have 2 pi here over beta for x dot. Notice this is a constant, 2 pi over beta, where our beta for this first segment is again equal to 30 degrees. So the velocity and acceleration equations are as follows. Recall, we're working with 4 boundary conditions, so we have a power of 3 on our position equation. We differentiate that and we get a velocity equation. Notice in this particular case we are differentiating with respect to time. And so when we differentiate our position equation, we get a velocity equation and our x's become x dots. We differentiate again to get our acceleration expression. And we notice that when we differentiate x dot, we do get 0 because this is a constant velocity profile. There will be no x double dots. An x double dot would mean that we did not have a constant for our x dot. But since we do, x double dot will be 0. And so we see our acceleration equation. And again, our x dot is equal to 2 pi over 30 degrees, or pi over 6 radians. So now it's time for us to determine the constants that we have here. We do that as normal, going back to our table. And for example, when theta is equal to 0, our s will be 0 and our v will be 0. And then we jump to when theta is equal to beta, or 30 degrees, v is going to be equal to 10 and a is going to be equal to 0. When we do that and solve for our constants, we end up with the following equation for our position. S is equal to 5/6 theta over beta squared minus 5 over 18 theta over beta cubed. So we have focused and finished our acceleration in this first segment. Now we can turn our attention to the constant velocity portion. From segment 1, we had s equals 0, v equals 0, and at theta equals 30, v equals 10, a equals 0. Now for segment 2, it begins at the end of segment 1, so it begins when theta is equal to 30, and the s that it begins at needs to be determined, and we have an s equals 5/9 here. Again, we have made some motion. We'd have to go back to our equation for segment 1, plug in theta equals 30 degrees, or theta equals beta 1, solve for the s, and plug it in right here for our table for segment 2 when theta is equal to 0. Again, this is a second segment. It's going to be the segment for our constant velocity portion, and it's an entirely new polynomial. At that point in time, our velocity should be equal to 10. We do not need to set any other boundary conditions. We do recall that the constant velocity portion goes through 180 degrees for beta equal beta 2. We don't set any other boundary conditions, resulting in 2 boundary conditions total, or a single order S function. So the highest power will be 1, meaning we have a line for our position equation, which we would expect, because a line for position means we're going to have a constant value for our velocity, and that's exactly what we should have. If we were to set any other boundary conditions, we'd have a second order position, and we therefore be having an increasing velocity, which we do not want. And so this is the final result for our segment 2 boundary condition table. These 2 boundary conditions result in the following SVA equations. So S is equal to C0 plus C1x, We differentiate that and we get v equal to c1 x dot, and our acceleration is 0 again because there is no x double dot. So when we differentiate this velocity, we get an a equal to 0 just as we desire because now we have constant velocity, no acceleration. For this particular part of the cam profile, our x dot is equal to 2 pi over pi. Again, this is theta dot over beta, but the beta for this particular segment is 180 degrees or pi radians. The resulting equation for segment 2 is as follows. So indeed, it looks just like a line where we have 5 times our slope plus our y-intercept. So here's our equation for position, and we differentiate this to get our velocity, and of course our acceleration is going to be 0, as is our jerk equation. Now we turn our attention to the deceleration phase, segment 3. From segment 2, here's our table. Segment 3 must match from the end of segment 2. So again, we go to segment 2, we find out what our S would have been, and we end up with 50 over 9 for that particular S. Our velocity is equal to 10, and our acceleration is equal to 0. Again, we're coming off a constant velocity portion. Our acceleration must be set equal to 0, and when we finish, we're going to have a velocity equal to 0. So at the end of segment 3, we are ready to accelerate from v equals 0 to v equals 10. So we must plug in a v equals 0 here at the end of our deceleration phase so we can be ready to accelerate. So we have 1, 2, 3, 4 boundary conditions. So we'll have a cubic in terms of our position equation. Note, if we would not have included the a equals 0 here, we would have ended up with an acceleration that was non-zero, which would not have matched our previous segment 2, and we'd have a discontinuity there. And so it's necessary that we have our a equals 0 in the beginning of segment 3. So again, we use a cubic equation for our position, c0 plus c1x plus c2x squared plus c3x cubed. Our velocity and our acceleration. Our x dot is 2 pi over pi over 6. It was this segment has a 30-degree beta, or pi over 6 radians. This results in the following equation for segment 3. Now we're ready to do our last segment. Here's segment 3. Here is segment 1. Segment 4 fits right in between. So for segment 4, we start by matching values from segment 3 above and from segment 1 below. Again, remember, whenever we're talking about a polynomial, we have to be concerned about what comes before and what comes after in CAM design. So we're looking at segment 3 before segment 4 and segment 1 after segment 4. So we'd expect to see 50 over 9, v equals 10, and a equals 0 at the, let me take a step back. Segment 4 starts at the end of segment 3. So we'd expect to see a v equals 0 in the middle of segment 4 at its beginning, and these two values would have to be determined. At the end of segment 4, we need to match up to here, and so we need to take this polynomial for segment 1, figure out what its acceleration is going to be, and plug that in. And so let's look at what we end up with for segment 4. Again, that v should be 0 at the start. The s equals 55 over 9, and the a equal to negative 240 are found by going to segment 3, plugging in theta equals beta, and finding out what this value is and what this value is for acceleration. And those are plugged in at the beginning of segment 4, the start of segment 4. At the end, we'd expect to see v equals 10 and we'd expect to see s equals 0 and v equals 0. And this value is found by taking this information for segment 1, plugging in theta equals 0, and finding out what that acceleration value is. And that acceleration ends up being 240. And so we have 1, 2, 3, 4, 5, 6 boundary conditions for segment 4, resulting in a 5th order polynomial. So here's our 5th degree equation. We differentiate to get velocity and acceleration. Our x dot is 2 pi over, in this case, 2 pi over 3, giving us a 3 for our x dot. The resulting equation for segment 4 is as follows. So then we can plot the entire profile, segment 1, segment 2, constant velocity, segment 3, deceleration, and segment 4 brings us back to 0, ready to start again. See our resulting velocity, acceleration, and jerk profiles. So this is a 4-segment solution to the constant velocity problem, and again we also have our maximum value shown just like we have done on many of our CAM designs. While this was a satisfactory CAM design, we could have made other choices. Consider that the motion outside of the constant velocity is not specified. We could have fit a single polynomial to the remaining motion. So if we go back to way back to our profile here, if we had started our profile here with the constant velocity portion, we could have set one polynomial to do the constant velocity, and then the second polynomial could have brought us back ready to start again. So instead of having 1, 2, 3, 4 segments, we could have done it with one constant velocity portion and then one big return from constant velocity ready to start constant again. In other words, 2 functions instead of 4. So we consider that the motion outside the constant velocity is not specified. We could have fit a single polynomial to the remaining motion after the constant velocity portion. Next time we will look at this solution.